Wofgang Ebeling, and he's going to talk about an algebraic formula for the index of one form on a real quotient singularity. Thank you very much.
Thank you very much. And first of all, I would like to thank the organizers, especially Marcelo, for giving me the opportunity to talk in this nice conference, in this nice location. It's my first time at IMPA. So I will talk on joint work with Sabir Guzenzade. And it is related to, it will be a generalization of the famous Eisenbart-Levin-Kimshashvili formula. Theorem. And so the name Kimshashvili has somehow to be added. So Kimshashvili did the same thing independently in the same year, 1977, but he published it in Russian, and therefore, as already Jean-Paul explained, it was only somehow later discovered that one should add this name here. So what is this theorem? Let me recall what this theorem is about. So we consider a map germ from Rn 0 to Rn 0, an analytic map germ with an algebraically isolated 0 at 0. This means that Fc inverse of 0 is equal to 0, where Fc is the complexification of F. Fc from Cn to Cn, 0 is complexification. Complexification of F. And let me denote the component, the coordinate functions of F by F1 up to Fn. And then one has the Milnor algebra, QF, which means one has the algebra of germs of analytic functions on Rn, divided out by the radical generated by the ideal generated by these coordinate functions f1 up to fn. And on this algebra, one has a standard, a canonical bilinear form given by the residue pairing. So if I take GH from this algebra QF, one defines BGH to be the residue of GH over F1 up to Fn, over the product F1 up to Fn, which is by definition 1 over 2 pi I to the power n times the integral over GH divided by the product F1 up to Fn dx1 veg dxn, and the integral has to be taken over the cycle given by the equations fk, absolute value of fk is equal to some small delta k. And so this gives a non-degenerate pairing bilinear form. And the theorem of Eisenbart, Levin, and Kimshashvili is that the degree of this map F this map as a degree, that the degree of this map is equal to the signature of this quadratic form, of this bilinear form. Signature B. So the signature is the number of positive eigenvalues minus the number of negative eigenvalues of this quadratic form. Now, this formula, this theorem, can also be interpreted as a formula for the index of a vector field of the singular point, of either a vector field where you consider the vector field given by fi d over dxi, or as the index of a one form given by omega is equal to sum over fi dxi. And also this Milnor algebra can be identified after the choice of a volume form with the algebra of germs of differential n forms, analytic n forms on Rn modulo the ideal generated by the omega wedge n minus 1. So this isomorphism is given by the choice of a volume form. And I will also use this interpretation of the Milnor algebra. And so then there's several generalizations of this formula. First of all, Gomez-Mont and Mabesic. They proved an analog of this theorem for the index of a vector field, for the index of a vector field on an isolated real hypersurface singularity. And together with Sabir, we did several attempts for one forms so to express the index as a signature of a certain quadratic form. Even one attempt I talked 22 years ago in Sao Carlos about this, but this is on somehow on a topological interpretation. And so in principle, our attempts failed up to now. So we have no analog for one forms. But the goal of my talk will be to give a generalization to a real quotient singularity. So first, let me first talk about the notion of index, which we use, the index for index of the one form. This is the radial index of a one form. Of course, this is inspired by the work of Marie-Hélène Schwarz. So we consider a subanalytic, real subanalytic set in Rn, V, the germ of a closed real subanalytic set and this is equipped with a Whitney stratification. So V union I. Vi is a subanalytic Whitney stratification. And we consider a continuous one form so it need not even be analytical continuous one form on V, 0, and this is in fact the restriction of a one form on the ambient space to this subvariety. And this is somehow one of the advantages to work with forms instead of vector fields, because this is defined, there's a restriction of a form defined on the ambient space. And contrary to vector fields, you don't have to care about tangency conditions. Sorry? Yes, restriction of the coefficients, yes, yes, of course. Continuous on Rn. So at this place we do not need, we only need continuity. Analytic will come up later. So, and what is the singular point of one form? P in V is called a singular point of omega if omega restricted to the stratum corresponding to the point P. So this is a stratum containing P. If this vanishes at the point P, it's a 0 at the point P. And a one form eta is called radial if it is a restriction, if the restriction to any analytic curve, so the restriction to the tangent vector of any outgoing analytic curve is positive. Curve phi from R greater or equal to 0, comma 0. Germ of a curve to V, 0 is positive. On the push forward of the tangent vector d over dt, so t is a parameter of R greater or equal to 0 in a punctured neighborhood of 0. So, and now I I want to define what a radial extension is. So let P be a point of the stratum Vi. So Vi is, by definition, also Vp, the stratum corresponding P. And let us assume that the dimension of Vi is equal to K. Then it is well known that there exists a diffeomorphism H from Rn, Rk, 0 to Rn of Vp P, and eta, the form eta, is called radial extension of form eta restricted to the stratum Vp if and only if eta there exists such a diffeomorphism such that eta becomes eta 1 pi 1 star eta restricted to Vp plus pi 2 star eta radical So somehow if you have the stratum so if this is Vp, then the form is equivalent to a form to eta on the stratum, and you have a radial extension, you extend it radially in the complementary direction. So pi 1 and pi 2 are the projections to the factors Rk and Rn minus k. So now, in order to define the radial index, we need somehow a perturbation of the form so omega is one form now on V0 with isolated singularity. At 0, and since it has an isolated 0, we can assume that it is defined on V intersected with a small ball of radius delta. And then one can show that there exists a one form denoted by omega tilde on V intersected with B delta such that first of all, omega tilde coincides with omega on the boundary, on the intersection of V with the boundary of the ball, B delta. So it's on neighborhood of S epsilon, which is the boundary. S delta, boundary of B delta. The second condition is that omega has only a finite number of singular points. Omega tilde has only finite number of singular points. And finally, at each singular point, singular point Q in V intersected with B delta minus 0, and Q is formed on the stratum Vi, and the dimension of Vi is equal to K, then omega tilde is a radial extension. Of omega tilde at Vi, restricted to Vi. And so this, we can use this construction now to define the radial index of a one form, namely the radial index of omega. It is denoted by omega v comma 0. We simply take the sum over the singular points of this perturbation omega tilde, of the indices, of the usual indices of this. So we take the sum over the singularities, singular points of omega tilde, of the indices of omega tilde, restrict to the smooth stratum Vp. So this is a smooth stratum, and we consider the usual index on the stratum Vp. So let me give an example. If omega is the differential of a function, so f is a real analytic function from now real analytic function, then the index, this index which I defined, is equal to minus the Euler characteristic of the Milnor fiber mf minus plus 1. So mf minus, so we are in the real situation, so we have two Milnor fibers, positive and a negative one. So mf minus is x, this, the set of all x in V is such that fx is equal to minus epsilon. And we intersect it with the ball B delta. And so epsilon is, delta and epsilon are very small numbers, and epsilon is especially small. And this is so-called the negative Milnor fiber. And if I have time, I will come back to a generalization of this formula at the end. So this is the radial index, and now I want to talk about real quotient singularities. So we consider a finite group. G is a finite group acting linearly on Rn, and hence also on Cn. We need this because we had this algebraic isolated condition. Therefore, it is, in all this question, it is necessary also to consider the complexification. So we consider the quotient Rn modulo G. One can show that this is a semi-algebraic variety. But it is, as I told you, it is also necessary to look at the complex quotient. And so, in fact, we look at the real part, W, of the complex quotient, Cn modulo G. And so what is this, how does this real part look like? So if the order of G is odd, then there's no difference. Then omega, W is equal to Rn modulo G. But in general, W is different from the real quotient. Namely, W, it can be shown that W is the algebraic closure of this quotient in Rg. So algebraic closure of Rn modulo G in Cn modulo G. And in order to describe this more precisely, and that you see that why in general W is different from Rn modulo G. So let me denote by pi the usual projection of Cn to Cn modulo G. And then we have the following proposition. We can describe the preimage of W under pi as follows. So the preimage pi inverse of the algebraic closure, so of W, is equal to the union of all group elements G of Rn G plus direct sum with I is the imaginary unit, Rn G minus, where Rn G plus minus is equal to the set of all x in Rn, such that G of x is equal to plus minus x. And let me give a quick proof of this proposition. So if we have a point P in Cn such that the equivalence class of P is such that Gp is equal to Gp bar, so it goes to the same image, to the same orbit, to the same class in Rn modulo G. This means that P bar is equal to Gp for some G in G, and of course G has even order, has to have even order. And so if we have a group of odd order, there are no elements of even order, so we do not have to care about this. So then we define U to be 1/2 P plus P bar. This is now an element in Rn. And G of, one can compute that G of U is equal to U. So U is in R and G plus, and we consider V equal 1 over 2 pi I P minus P bar. This is also an element in Rn. And for this element, G of V is equal to minus V. So V is an element in Rn. G minus. So altogether, we can write P as U plus IV. And this shows the proposition. So now we consider a form on W. So omega should now be a real analytic one form on W. And we consider the pullback omega star is equal to the pullback via the mapping pi of omega, and this is now a G invariant real analytic one form on pi inverse of W, comma 0 sitting inside Cn, comma 0, but inside pi of 1 of W, there's Rn sitting, so thus it is a G invariant form on Rn inside pi inverse W, 0. And we now can consider omega, capital Omega, omega star. This is capital, we consider as before, we consider n forms on Rn, modulo now omega star, wedge n minus 1 forms on Rn. And this is equipped with the residue pairing, which I defined at the beginning of my talk, with the residue pairing which I denote by B omega star. And now G acts on on this module, and also on G omega. It acts on omega n Rn, comma 0, and also on this quotient. And we consider omega, capital G, is the G invariant part. Of omega star. And we can consider the restriction of the residue pairing to this G invariant part, which I denote by B upper G omega star. This goes from omega star across omega star across G to R. This is the restriction of this bilinear pairing, and one can show that it is easy to see that this is also non-degenerate. And now the main theorem I want to talk about, this is theorem of Ebeling and Seade. So it is published in 2000 18 in Mathematische Nachrichten, and also there's a smaller version in functional analysis and its application. And I take the easier, so there's somehow a simplification, and I consider this simplification. So the general result is a little bit more general, but then I have to talk about equivariant radial index, and I do not want to talk about this. So this is a slight simplification. Now we assume that G is abelian. This is essential for our proof. And omega is a real analytic one form on W, 0 with an algebraically isolated singular point, with algebraically isolated singular point. And so germ of a one form, always draw, I omit, if I'm talking about one form, I mean germ of a one form at 0. And then our result is that the index of omega on W, 0 is equal to the signature of this form BG of omega star. So of course, so omega and omega star. So one problem is that we do not know whether it is possible to push forward a differential form. But one can push forward a function. So as a corollary, we get that if f is a G-invariant analytic function, on Rn, then we have a push forward f check on the quotient Cn modulo G, and then we can formulate this, that the index of the differential of this push forward on W 0 is equal to the signature of df G. So in the remaining time, I want to say some words about the proof of this theorem, and if I have time, of an application. So the proof has several ingredients. The main ingredients are laws of conservation of numbers, of conservation. Of numbers for both sides of the equation. So for the index, so this means for the index, this follows more or less from the definition, namely if omega tilde is a small real analytic deformation, of omega, then the index of omega is equal to the sum over the singular points of omega tilde of the indices of omega tilde WP. Note that in contrary now these are general singularities, so in contrary to the old formula, to the definition, here was the index of regular, the usual notion of index, here's already the notion of radial index. And for the signature, we have the formula that the signature of B, of this B omega star G, splits as a sum of all P singularities of omega star tilde, so the pullback of omega star tilde, of the signature of B GP, Q, GQ, no, GP, GQ, omega star tilde, Q, where Q is in the inverse image of P, and the signature is computed on GQ invariant part, where GQ is the isotropic group of the point. So GQ is the isotropic group of Q, of the point Q. So this formula is more difficult to derive, and this shows that somehow its splits correspond to smaller, in general, smaller groups. So these isotropic groups are smaller groups, and we will use this at the end to do some induction. So the second part, second ingredient, is a deformation of one forms. Deformation 2, one forms, with only non-degenerate singular points. So this one would, of course, try, if one has these laws of conservation, to deform it into forms with the most simple type of singular forms, which is a non-degenerate singular point. So omega can be, and one can show that omega can be analytically deformed to omega tilde, such with all singular forms of omega tilde, with all singular points of omega tilde star are non-degenerate, except which split from the origin. Non-degenerate means, of course, this A1 type singularity. So if omega is non-degenerate, so if omega is such a non-degenerate form, then the Milnor number is equal to 1, so the dimension of omega star is equal to 1, and also the signature of B omega star G can be easily computed, namely it is equal to 0 if G is not contained in SL and R, and it's equal to plus or minus 1, which is equal to the index of omega star on Rn. 0 otherwise. So this is easily computed, but it is more difficult to compute the index, the radial index of a non-degenerate one form. And it's even difficult to give combinatorial formulas for it. And therefore, we use another method, and therefore, we need the assumption that G is abelian. Namely, if G is abelian, then G has only one or two-dimensional real representation, irreducible representations. And so first, and now we reduce reduction to one-dimensional representations. So here we use that G is abelian, so only one or two-dimensional irreducible real representations. And now it is possible, it's not so easy, but it is possible to reduce the computation of the index of omega zero of such a non-degenerate form to these representations, to those representations, which contain only one-dimensional, non-trivial representation, to those representations of G which contain only one-dimensional, non-trivial representation, one-dimensional and non-trivial. And then the last step, and now we are reduced to the case of one-dimensional non-trivial representation of one-dimensional non-trivial representations. And then we consider a special form, and this is also for which we can compute the index. Namely, we consider omega 0 is d of sum over xi to the power 4. And this is positive on all non-trivial one-dimensional representations. And therefore, we can compute the index. It's positive on all non-trivial one-dimensional representations, and therefore it is a radial form, and one can compute that the signature of B omega 0 star of G is equal to the index of omega 0 W 0, it is equal to 1. And now this form omega 0 can be deformed to any non-degenerate. One can show that omega 0 can be deformed. To any non-degenerate. And then the proof of theorem 1 of the theorem is completed by induction. On the group order. By induction on the group order. So I have still some time, I see. Therefore, let me finish by giving an application of this result. And I consider now, first, I consider the complex n space with a G action, and F should be a complex analytic, holomorphic, G invariant, holomorphic function germ. Holomorphic function germ with isolated singularity. At 0. And let me introduce some notations. So for an element G in G, I denote Cn to power G is a fixed point set of G. Of G. Its dimension is denoted by small ng. It's a dimension. So this is the fixed point set is, of course, a coordinate space, linear space, subspace. And therefore it has a dimension. This dimension is denoted by ng, and let me denote by f upper G to be the restriction of f to this fixed point space of G. So fg goes from Cn G, 0 to C, 0, and one can show that this singular has again an isolated singularity at the origin. And let me denote by MFG the Milnor fiber. Now we are in the complex situation, the Milnor fiber of Fg. Then there's the so-called quantum singularity theory, formulated by Fan, Jarvis, and Ruan, and they have the definition of a quantum cohomology group of Fg of the pair. So, Fan, Jarvis, Ruan give the definition of a quantum cohomology group of the pair of such a pair Fg, and it is denoted by script F, G, and it is the direct sum over all group elements of G of H of the Ng minus first cohomology group of the Milnor fiber of Fg with complex coefficient, and one considers the G invariant part of it. And we denote by omega Fg is the module of differential Ng forms on now holomorphic Ng forms on Cng, 0 modulo df G wedge omega Ng minus 1 Cng, 0. And now one has a canonical map somehow from omega F G C to the cohomology group of the Milnor fiber. Canonical. Namely, if I take the form eta, I consider the form eta divided by dfg. I take the de Rham cohomology interpretation, I take eta divided by dfg. So this gives an isomorphism. This shows in particular that they have the same rank. And even so, of course, here on this module, one has the intersection form of cycles, of vanishing cycles. Here one has the residue pairing, and it is a question, how are these related? Even these authors claim that the residue pairing goes to the intersection form here, but in our paper we give a counterexample that this cannot be true, because the intersection form is skew-symmetric in one case and symmetric in the other case, depending on the dimension, whereas the residue pairing is always symmetric. It's a symmetric bilinear form. And so this canonical isomorphism respects the G action. So now I come to the application. Now I consider the real situation again. Let F be a real germ, F from Rn 0 to R. Be a real G, and let G be abelian because we want to apply our theorem. And I denote by Q F small g, the sum over all G. Sorry, this should be capital G. Sorry, capital G sum all G omega F G G. So somehow I take this construction of the quantum cohomology group I take for the corresponding algebra and for the real algebra. Q omega Fg was the real, the G invariant part of the real. Fg is now real. And the quadratic, the bilinear pairing dFg is defined by taking the corresponding sum of all G by B G D Fg. And now I want to relate the signature of this pairing with an index. We also can relate it with an index, but in this equivariant version of index. But it boils down to, if one considers the Euler characteristic, which was an interpretation of the index for the case of a function, then we get a generalization involving the so-called orbifold Euler characteristic. So I have to define what is the orbifold Euler characteristic. So this is also is a definition initiated by physicists. So we consider a topological space with a G action. It's a good topological space with a G action and then the orbifold Euler characteristic. Is defined as follows. So it's denoted by Chi orb of x, comma G. It is 1 over the group order, and then the sum of all commuting pairs of elements. So of all G1, G2, so that G1, G2 is equal to G2, G1 of the Euler characteristic of the fixed point set of G1, G2. So this is the fixed point set. Fixed point set. Set of the subgroup G1 generated by G1, G2. And we need the notion of the reduced orbifold Euler characteristic. So Chi orb bar of x G is equal to Chi orb x G minus Chi orb of a point. Topological space consisting of one point, G. This is reduced Euler character, reduced. And in the case that G is abelian, which we case G is abelian, then the orbifold Euler characteristic of a point is simply the order of the group. So simply in this case we subtract the order of the group. And finally the corollary of the main theorem is that the signature of B df is minus the orbifold, the reduced orbifold Euler characteristic of the negative Milnor fiber of of G. So remember, we had this formula minus chi plus 1, and this plus 1 in the case, original case with the Milnor fiber is connected, so we have just to subtract 1 point, and minus subtracting 1 point means plus 1, so this agrees, in particular in the trivial case, that the group G is trivial. It agrees with the old formula. So thank you very much for your attention.